This video will look at the same truss that we analyzed previously, but this time the load is inclined at 30 degrees from the vertical. 10 kip load, 30 degrees from the vertical. As with the previous problem, we need to find the reactions. Pin support on the left side, roller support on the right side. So we have potential for a vertical reaction on the right-hand side, a vertical reaction on the left-hand side, and a horizontal reaction on the left-hand side. This time, because we have a horizontal component of the 10 kip load, we will have a horizontal reaction. So we'll call this R left horizontal and R left, R left vertical and R left horizontal. Now we first need to break the 10 kips into components. We can solve this by summing moments if we knew the exact perpendicular distance, which would be something like this. If we computed this distance, we can find that force directly. However, that's mathematically, geometrically much more complex than simply breaking this down into its horizontal and vertical components. So the 10 kip load, and we're doing this trigonometrically, so we don't have to worry about drawing this exactly perfectly. So if we call this load P as our applied load, we have P vertical and P horizontal. The angle, 30 degrees. Since we know the sine of 30 degrees is opposite over hypotenuse, we can say that P horizontal over 10 is our magnitude of the horizontal force times the sine of that angle. So P horizontal equals 10 kips times the sine of 30 degrees, or 0.5. So the horizontal component is 5 kips. The vertical component we find similarly. By taking the cosine of the angle, we know the cosine of 30 degrees is the vertical component, P vertical, over 10 kips. So P vertical times the cosine of 30 degrees, or 0.867, .66, 8.7 kips. So, looking back to our original truss, if we were to mark these in here, vertical 8.6, horizontal 5, we complete the same calculations as we do for any problem, starting off summing forces horizontally and vertically. So if we do the horizontal force first, it's our simplest one. We call forces to the right positive. We have R left horizontally minus 5 kips. That also all equals 0. R left horizontal has to be equal to 5 kips. There's no other forces acting horizontally here. summing forces vertically, we'll again use down as positive. We have the 10 kip force, the 8.66 component of that force, plus R left vertical, plus R right equals 0. Those are the only forces that act in the vertical direction. So all we can say right now is that R left vertical plus R right equals 8.66 kips. To solve for this, we have to sum moments. We'll again choose the left-hand side, and we'll call clockwise positive. Now, a big difference than the last time. We only had a vertical acting force last time. Now we have a horizontal acting force, which is the horizontal component of our sloping incline force. What that means is that with respect to the left-hand end, we now have 3 forces that rotate about that end, not just 2. We have the 8.66 force, moment arm is 7 feet. We have, again, the right-hand reaction with a moment arm of 11 feet. But we also have the 5 kips, the horizontal component of the 10 kip inclined force, and its distance, didn't mark it on here, is 4 feet. So we must consider all 3 of these. So with respect to the left-hand end, let's start with the 8.66 kip force. 8.66 kips, its distance is 7 feet. With respect to this point, it's tending to rotate in a clockwise direction, therefore it's positive. We have the horizontal 5 kip force. Its moment arm, the perpendicular distance between it and the point we're considering, is 4 feet. Its tendency to rotate is counterclockwise. If it were tied onto the left-hand side, it would rotate in a counterclockwise direction. Therefore, it's negative, because that's what our sign convention says. Anything that's counterclockwise will be negative. R right also goes in a negative direction, and it's at 11 feet. So now we can solve for this. We have R right equals 8.66 kips times 7 feet minus 5 kips times 4 feet divided by 11 feet. And that comes out to 3.7 kips. R left is simply the difference between the vertical forces using this equation. R left is 8.66 minus R right. Go back to sum of the forces vertical equal to 0. .66 kips minus 3.7 kips equals 4.97 kips. So we'll round that up to 5 kips. Only a 30-pound difference. So very interesting here, we ended up with 5 kips horizontally and 5 kips vertically under this particular loading. Now we have this analyzed. The next step is to compute the force polygon from the form diagram, and that will be our next video. Now from this point we can construct our force polygon. And to do this I'm going to go back to my original 10 kip force. We can do this with the components if we want to, but it'll simplify things if we just go back and go to the 10 kip force. Now I'm going to, just for clarity, erase these forces here because we don't need them anymore. And this is going to let us see that we only have 4 spaces. We have the space between the left-hand horizontal reaction and the 10 kip force that we'll call A. We have the space between the 10 kip force and the right-hand reaction we'll call B. Between the right-hand reaction and the left-hand vertical reaction, we call that C. Then between the left-hand vertical reaction and the left-hand horizontal reaction, we'll call that D. And one panel in the middle, just label that 1. We'll again do this diagram at a scale of 1 to 30. In other words, 1 inch is going to be equal to 3 kips. Now our original force of 10 kips is acting at 30 degrees, so we need to transfer that force at 30 degrees. I need to move up here, we have enough room. Again, it's very important to do this as accurately as you can because the accuracy of your result is going to be dependent on the accuracy of your construction. So that establishes the angle of my force. The magnitude, I scale off of my scale at 10 kips. And the force goes from A to B, so I start at A, then I go to B. B to C is a vertical reaction, so that's strictly a vertical line. Don't really need to transfer anything to do that. Just simply line this up vertically. That's why I like to use the graph paper. So point C is located at distance 3.7 kips. So we go 2, 3, 3, 5, 3, 6, 3, 7. Right here. That's point C. And then 5 kips, of course, takes us back. Point D, and then 5 kips over, if we've done everything correctly, this should come out to 5 kips. And we can see it slightly off, but it's pretty close. And we go from D to A. Now we can read our forces directly. So again, A to B, this is our 10 kip applied load. From B to C, that distance represents our right. From C to D, this is our left vertical. And then from D to A, this is our left horizontal. Now we need to find these various points. We have a vector A1. It slopes at an angle. We transfer that angle. This way. So this is vector line A1. Then we have vector B1. Going this way. And then the horizontal vector C1 going this way. And it's a little bit off, but it's fairly close. This is point 1 that's shared between all of them. A1 and B1 intersect at 1. And C1 also intersects at point 1. So you can see a very, very different looking diagram than we had last time, simply by changing the inclination of the load. Exactly the same truss. All we've done is taken the 10 kips and angled it down. So now the load line changes considerably. Our load line isn't just a straight line, it's a triangle. So we get the resultant forces simply by scaling. Number A1 comes out to just about 10 kips. Member B1 a little bit under 5 kips. We'll say 4.9 kips. And then member C1 is about 3.5 kips. And in the last video, we will look at the sense of these forces, tension and compression. Now that we've completed our force polygon and we've located the magnitude of all of the forces, the last thing is to find the sense of those forces. Again, we do this by the same labeling convention. If we look at the lower left-hand joint, member A1 is called A1 because reading the joint name in a clockwise direction across that member says that we go from A to 1. So it's a movement from the upper right to the lower left. We see again that it is compression, points towards the joint. If we looked at the upper member, upper joint, this member would be called 1A. Reading the joint name in a clockwise direction, the 1 comes before the A. Moving from 1 to A, we go towards the joint, therefore it in fact is a compression force. Up 10 kips. Looking at the right-hand inclined member, we have B1 is the name at the upper joint. B1 goes from B to 1 towards that joint, meaning that it's compression. And we can confirm that by looking at the lower right-hand joint. The name of that member would be 1B. Moving from 1 to B, again we go from the upper left to the lower right towards the joint, therefore it is compression. 4.9 kips is the magnitude. And lastly, we go back to the left-hand joint. 1C would be the name of the member with respect to that joint. we go from 1 to C, we're moving away from the joint. If we move away, we're pulling, meaning that this has to be a tensile force. And again, if we look at the right-hand side, the name would then be C1. We go from C to 1. We are again moving away from the joint. So C1 is 3.5 kips in tension. Now you can see how this is about as small as we can make this diagram. It's getting very crowded in here. We can make the measurements, but it's getting a little bit tight to do all of the nomenclature and stuff. So even a little bit bigger than this would be an ideal size. But that completes the diagram. The process is the same as what we did last time, but it looks different. Every time we change our loads, every time we change our shape, the diagrams change, but step by step by step, it's always the same sequence. If you stick with the steps, if you don't jump ahead, if you don't skip something, then you'll do just fine.